So let's start the session. Okay, and very good evening to you all. And I hope that all your weekend was been very great, and hope in future also your evening will be very nice. Now let's start the session. Today's topic, what we are going to start with is steady state thermal analysis of a 18650 cell. Okay. So before that, coming to that whole analysis, I'll just brief through you about what are we doing, like why this requirement is there. Okay. So the thing is, why we requirement? Like, why do we need to manage the thermal management? Like, we do have like batteries in our automobiles. Like, you all have your cars and scooters, your motorcycles. You have your lead acid battery, but you don't require such proper, implication of thermal management. You just have a battery case there, over there in your 12-volt battery pack. You have in your four-wheelers, in your two-wheelers, but you don't require the thermal management. So why this such thing is required in a lithium-ion battery on an electric vehicle? So the only thing is that we all know that electric vehicles have a tendency to catch fire. Okay, that's jokingly. So why does the thing happens? Like we all know that a lithium-ion battery has an optimum battery working temperature. Okay, so what the thing is that whenever uh, like it has a working temperature, if it goes above that, so it heats up very quickly. We do have very pros of lithium-ion battery, like they have good charging efficiency, they have a high specific energy density and everything, but they do also have such poor thermal management. And for the safety in life is as in terms of safety, the safety of the battery and the vehicle, and life, like as the battery gets heats up. Okay, like for example, if I have a battery pack and it's getting heated up very precisely. Okay, so what will happen, for example, if I have a two-wheeler, okay, and it has a range of around 80 kilometers at a single charge, okay, and I don't have a proper thermal management, like my manufacturer didn't thought of such thing, okay, and it's a Chinese product to be very, okay. So what happened, first when I bought the vehicle, I drove it, I discharged it, I got a range of 80 kilometers, okay, my battery got heated up. Next day, when I charged my battery, I went to office, come back over the distance I covered to discharge my battery. My whole range that I got from 0 to 100 to 0% came to 74 kilometers. Okay, might be an issue. But it will be my everyday case. Like whenever I'm charging, discharging my battery, my range will get reduced. Why? Because the battery life is getting reduced because your cells are getting heated up and the charge that is, its life is getting reduced day by day. Okay. Performance is like what I told you, that the amount of, if you go with, there's no proper thermal management. So you won't be able to reduce high amount of current. For example, a standard cell has like at 1C charge. Okay. If I just let me do one thing. Let me have this on PPT version. Okay. It'll be easy for you all. I'll just download it. Okay, let me have a question for you all by the time. So what do you think, like if you have some knowledge, so the manufacturers that we have in our country, so at what C rate do they work on? Like they prescribe you to work on, like at 1C rate, 2C rate. You might have heard such C rates. So what do you think? What kind of C rate do you suggest to work on? Any answers? 1C. Okay, great. And 1C rate, yes, very true. 1C rate. And what is the limit that you can take your cell to?
2C.
2C rate. Okay. Okay. So two, yeah, 4C exactly. Yes, me. 4C rating. Yes. Like there are some technical, like when you go with sheets, then you have such 2C and 4C rates over there. Yeah. Okay. Not now. I'll just talk about here. Okay. Sure. Okay. Now what we have is performance. Okay. So what this performance is that, as I told about the C rating. Okay. So for example, if I have a motor, okay, and a motor is at a range of around, like if that motor gives 100 ampere, 100 amps, it will provide 10 newton meter of torque. Okay. And if you provide 200 amps, it will give you 30 newton meters of torque. Okay. So that ampere rating that you're providing that motor, that is provided by the battery pack. Okay. So that cell is providing you. Okay. So if you take your cell without any thermal management and you reduce, you just induce 200 amps over there. So your cell will heat. So that will decrease the battery life. But if you want that from that only battery pack, you want to supply 200 ampere hour. So you have to provide thermal management so that it cools down your battery. If your battery is working in a very cool temperature, okay, so there won't be issue of on your performance, on your life and everything. Okay, so that's why the four-wheelers that we have, okay, uh, if they were working in one CDT, so they require a very huge battery pack. That's why they have very compressed size of battery pack and they have thermal management. For example, talk about the Tata Nexon EV. It works on liquid cooling system. Okay, like because the 300-volt battery pack that it has, okay, and everything operation it has. Even though what the architecture right now is following by the uh, Ziptron technology in the Tata Tigor EV, it works on 72 volt. So you can start if the voltage is less. So if they're working on 20 kilowatt, 25 kilowatt motor. Okay, if the voltage less, so it is very like suggestive that there will be high current amount over there. Okay, so that's why these battery works on very high thermal management aspect. Like they have liquid cooling, they have forced induction cooling as well. Okay, that's why these things are required over there. Then we have charging and discharging. So what I have told you, that you'll be having issues if you not implying proper thermal management. So the charge and discharge will be going on decreasing. Okay, you will not getting that efficiency as well. Okay, cooling battery at fast charging and large current. Okay, so what does this thing means? Okay, so we all have know about that. We have fast chargers, DC fast chargers that works at 15 kilowatt, like that, 30 kilowatt. Okay, and these chargers, so what happens when you for fast charging, like you have in your phone. Okay, you all have noticed that when you use fast chargers, so your phone gets heated up. Okay, it gets heats up. Okay, so what the reason is that at that for that minimum amount of time to charge a battery in 15 minutes, 16 minutes, huge amount of current is given to the battery for charging. Okay, so this current will induce heat due to Joule effect. That's why when such high charging is provided, the whole charging structure, it manages to cool the battery so that it doesn't get heated up. That's why there's such thermal management required to focus on. Okay, now I'll talk about the different type of chemistry that we have in lithium-ion cells. Okay, just to short brief. Okay, now what we are seeing is that here is six type of different graphs. Okay, so these are like what we have is lithium-ion cell. We have six chemistries that we use. Okay, and these chemistry are used for different purpose. Okay, so the first one is lithium cobalt oxide. Okay, these are the cells that we use. That we have in the small projects we used. Okay, like we have lithium-ion cells that we use earlier in our small science projects and everything or we have in our torch over there that can be chargeable. These are those cells, lithium cobalt oxide. So what it has huge amount of specific energy. See, this is called a spider graph. Okay, and what these things show is that specific energy. These are the I can say the pointers that we can call out. Okay, these factors: specific energy, specific power, safety, performance, lifespan, and cost. And this shows that is that the score of the factor. Okay, so if I talk about specific energy, so it has a very good amount of specific energy, but less specific power. Safety is also less, which means that it can catch fire. Okay, it has a good performance. Lifespan is less, which means less charge cycles, and then a good amount of cost, like it's cheaper. Okay, then you move on to lithium manganese oxide. Okay, and in this, what we have is we have specific energy is okay, specific power is good as compared to it, safety is good, performance is less, lifespan, which means less charge cycles, and it is moderate in expense. Okay. Similarly, for every if what we usually go with is NMC, nickel, magnesium, cobalt. Okay. And in this, what we have is specific energy is good, specific power is also good, safety is also good, performance is also adequate, lifespan is also good, and the cost is also at moderate. That's why this cell is highly used, which we have like 18650, everything we use such cells. Okay. Then we have LFP. Okay. Now in LFP, so this is what is called lithium iron phosphate. Okay. So these two cells, if I call NMC and LFP, these two are highly used in electric vehicle market in India right now. Okay. We do find for cylindrical, for prismatic, we have such cells. But if I talk about what is difference, so if we just check over here, specific energy is low, but with high amount of specific power. Okay. And safety is also good aspect of here, performance good, lifespan is very good, and cost is also good. Okay, moderate. So what differences? Like these battery is majorly used in two-wheelers. Okay, NMC, highly used over there. Why? Safety is moderate over here. Okay, specific energy, which means that based upon the mass of that. Okay, so it's lightweight over here. Power is okay. Performance adequate. Lifespan is good. Okay, and cost is moderate. So that's why these cell is using NMC in two-wheelers. Now for four-wheeler, what we require is safety is a major concern. Safety and lifespan. Okay. Like because you won't require that after 2 to 3 years you want to change your battery pack. Okay. Because a battery pack alone can cost you 5 lakh rupees. Okay, for a four-wheeler. So like what we have is usually that after 3 to 4 years a person changes passenger vehicle. Okay, but that vehicle is in running condition because an engine has a life of clocking to 1 lakh to 1,50,000 kilometers. Okay, but if lifespan is low, okay, if over here, so that will be a major issue. Like that car won't be able to use for second-hand market. Okay, that's why we require a battery that has good lifespan. Okay, safety is an important concern over here because what we have is that's at such huge amount of cells because in a four-wheeler there's around more than 1,000 number of cells are used over there. So that's why safety is more. That's why these cells are used over here. Then we have nickel, cobalt, aluminum oxide. Okay, so this is one thing, and then we have lithium titanium oxide. Okay, this is on R&D phase. It's very expensive, as you can see, cost over here, but it has huge amount of you can see over here. So, by this is the way how you can look at the cells. Okay, the next what I have is cell construction. Okay, like what we have. So here we have three types of cell construction. First is the cylindrical. Okay, then uh, the other is the pouch, and then we have prismatic. Okay, so in cylindrical, what we have is it is the most common used cell in lithium-ion batteries. Okay, lower cost and production rate. Okay, so this cell is very extensively used in the Indian markets. Why? Because you can open your small manufacturing in a room. Okay, like you can assemble the cells properly. These are very safe to handle. Okay, there's no such quality testing and everything. Short cells. Okay, and even the transportation is very easy for them. Okay. Low energy capacity. So the range of these cells start from 2000 mAh to clocking around to 3000 mAh. Okay, even you get 6000 mAh, but that's a different category. But it's a very low energy capacity cells. Okay. Then we have uh, pouch cells. Okay, so lighter in design. Okay, expensive to manufacture, low energy density, poor thermal management. Okay, prismatic cells. Now we have pouch cells. Okay, so these are lightweight, high packing efficiency, good cycle life, prone to swelling. Now these pouch cells are extensively used in four-wheelers. Okay, like for the bus bars that we talk about. So this is where the bus bars are put at these tabs. Okay, and they are very lightweight. Okay, high pack efficiency means like with uh, like there's with when the array of such battery packs are placed over there, they're very lightweight, the dimensions are very less, so you can assemble lot of batteries all together in very small space. Okay, so like what we have, because in cylindrical cells we have to add holders, we have to reduce space over here as well, but this have very high pack efficiency, good cycle life. But one thing is they are prone to swelling, that they swell, okay, after heating. Like for example, you have in your and we used to have, Samsung phones, or at 2010, or at Micromax phones or Lava phones, you have seen your battery gets swollen after some time. These are the reasons that we have. Okay. Now, if I talk about the 18650 cell construction, okay. So what the cell construction is, because now we're talking about is the cell. Okay. So you can see here what I have is negative electrode. Okay. That negative is the anode. So what we have is the graphite. Okay. The positive is the lithium ion iodide. Like if we are looking, it might be cobalt oxide, might be the NMC cell, anything. We have separators. Okay. Separators are one that keep these electrodes and cathode, apart from each other, so that the ions can be reused. Okay. Then we have PTC. Okay. So PTC devices to cut off like the whole cell, when it's like a device that is used to when there's an internal short circuit. Okay, so to protect the cell, like when, for example, if you're using high rating, you're rating 4C, 5C, okay, understands that now the whole cell is getting, its cell is getting very overheated. So it discharges the positive cap, okay, from this electrons in every chemical reaction, so that there won't be no any further exchange of electrons or the current over there. Okay, that's why this device is used. And then we have casing, insulation, everything. Okay, now heat generation. Okay, so this is an important parameter. Like today, I will talk only about the basic things. We won't be getting in very detail. So Joule heating is considered as a parameter for heat generation in battery pack. Okay, so heat generation. So in watts. Okay, so Q, that is the energy, is equals to current, the square of the current into the internal resistance of the cell, okay, or the resistance of the that what we are dealing with, electrical component. Okay, so whenever this, like, see, internal resistance is always constant for any material. Okay, like for it varies with material, but for a material it never changes. Okay, but this current, this is a very variable property. Okay, this is your fixed, this is variable. Okay, so if you increase this current, you can see, so if my current is doubled, so due to the square, so my heat ratio will be increased by 4 times. So you can see how this current plays an important role in the heat generation of any component. Okay, and where this heat generation battery pack reduces in cells, okay, in bus bar and BMS. This is where, okay, temperature, depth of, so this is what affects temperature, depth of discharge, open circuit voltage, temperature. This is what monitors. So these things where we focus on, when we focus on, like we start with the basics, so we have to follow that the cells, okay, like the heat generation up, like at this place, heat generation will take place, bus bars as well, because these are the conductors that are, exchanging the whole series current from these, what I say, the cells, and then the BMS. Open circuit voltage. Okay, Meet. Open circuit voltage is like the, if I talk about the simple, if I talk in a very, very layman language, okay. So when you you have a battery, you connect two wires, okay. And the voltage that you're getting from that circuit, from that connection is called open circuit voltage. That is the very fresh voltage that you're getting from your battery, okay, cell. Depth of discharge. Okay, depth of discharge. Okay. So what is DOD? DOD is called depth of discharge. Okay. So what I have is, yeah, depth of discharge is something we all know that not everything works in 100% efficiency. Okay. Like if we talk about engine, we talk about motors. Motors even have 90% of, efficiency. Transmission has a 70-80% of efficiency. Same what we have with our battery packs, okay, or our cells, lithium-ion cells. Every battery has its own depth of discharge. Which means if a manufacturer says to you that this is my cell and you have 100 ampere hour, okay. So if I just, okay, if one says that I have 100 ampere hour cell, okay, lithium-ion battery pack, okay. So never take this as 100 ampere hour. Okay. It will always be like for lithium ion cell, it is taken as 0.85. That is the degree of discharge. Like if this is your cell. Okay. This is your cell. Okay. Just consider it. Okay. This is your cell. Okay. So if you think that this is 100%, this is 100%, and this is 0%. Okay. That your energy, and he's saying 100 Ah of cell. Okay. So your cell won't have this, right? It would move with 100 to 0 like that. It has some depth of discharge. Like it has an energy starting from this 85%. Okay. So it will have it like it might be from, like, I'm just giving example. It's gonna start from here and then end some 15% before that. Okay, like there's some space left over there. Not everything is consumed completely. Okay, if everything is consumed, that will be completely exhaustible. And you cannot, regenerate anything that is completely exhaustible. Okay, that's why we have depth of discharge. Okay, so if it's saying that you're getting 100 Ah, so you should thought that your battery pack is actually working at 85 Ah. Okay. So remember, when you're working on projects, everything, if you're even planning to customize a battery pack here, for example, if in future you're planning to retrofit your vehicle, okay, and you have to optimize your own battery pack. So always take this consideration. People do, take without this depth of discharge, they calculate their range, okay. They assume that they're having 100 kilometer of running charge, okay, but they might get 80 kilometers like that. So they blame the motor or they blame something like that. But the only thing is that you've not taken the depth of discharge. So always, if you have taken 80, if you considered that you want 100 kilometers, so plan a battery pack that can move it 120 kilometers. Okay, so you get that 15% as an added advantage. Now I'll go. Now I'll talk about convection. Okay, so what is this convection? Okay, it's just a simple way of telling, like, what happens if I told you about, like, heat convection is a process of heat transfer by physical movement of fluid molecules from one place to another, in which there exists a temperature gradient. Okay, so in this example, if I talk about what happens over here is, like, you have a vessel, you're boiling a water. Okay, now the molecules present at the beneath, okay, they will start getting heat because they're close to the stove. Okay, and they're getting the fire, now they're getting heated up. Okay, so these molecules, as they heat up, so they're due to the gas formation, they go travel upwards. Okay, they'll go upwards. Okay, and at the above we have the molecules that are at cold, that are cooler than that. Okay, so these will exchange temperature because now this is hot and this is cold, so they will exchange temperature. Okay, and the cold molecules will meet with hot, they will have, this whole, and the whole thing, if this keep getting, they keep getting temperature high at constant level, so the whole thing will burn up, like it will start boiling. Okay, this is what is called convection. If I say in a very small way, like for example, why do have, like, if I give you very practical solution. Okay, you all have right now, you're working on your laptops. Okay, you all have in your laptops. Okay, you all have laptops. Okay, your processor gets heats up. This is your processor, just think. Okay, you have a fan, right? You have a fan. You have a fan, and start making noise over there, like even though mine is working on a single fan, right? Okay, now once I start my ANSYS, it'll start screaming right now. Okay, so what happens once this your processor gets, heat up due to clock speed increase and everything. Okay, the fan will start flowing in air from outside. Okay, so this air will try to cool down it. Okay, so as this is heat, as this is hot. Okay, this is hot, this is hot. Okay, now just think this is my processor. Okay, and I'll just use this black one as my fan. Okay, now what happens, this is red, this show that it get heated up. Okay, now my processor is right now, it's working at a temperature of from 30 to, it's now 60 degrees Celsius, 60, 70. Okay, it's hot now. Okay, hot. what my fan will do, it will flow in some air from the room temperature, okay, to this processor, okay, and this will cool down the whole processor. Okay, so we know this phenomena. Like even though if you take a cup of tea, that's very lukewarm or very warm. So you try to, blow air into it in your cup so that it gets cooled down. Okay. So what's the reason behind it? So what happens? The molecules, these cool molecules interact with your solid molecules, these fluid molecules. Okay. And when they get interact so much, it's a temperature gradient. That is, if this is at 20 degrees Celsius. Okay. This is at 20 degrees Celsius. And this is at 60 degrees Celsius. Okay. So you'll get a gradient of 40 degree. Okay. So it will cool down your, I guess this is understood like 40 degrees Celsius. Okay. This is cool down your whole processor. So this is the exchange of, heat gradient between these molecules. Like we have three transfer. One is convection, and radiation. So conduction is possible with solid, uh, solid matter. Okay. For example, if for the same stuff, okay, now the whole this utensil or vessel is very warm. Okay. If I place my hand on it, I will feel that burn. Okay. So that heat transfer is called conduction. Okay. And if I stop this, like if I place this same thing, okay, this hot vessel into my refrigerator, okay, with the cool air of the whole refrigerator, okay, it will cool down that vessel. That is called convection, because now the fluid is involved. So whenever there is fluid involved, okay, that is called convection or the heating process. Okay. And this is the formula that is called, just use a red mark in our color. Black is okay. Yeah. So this is the formula that we're going to use. That is called Q is the heat transfer per second in joules. Okay. H is the convection coefficient. Temperature difference is called del T. That is from the, if I just take this T as hot body minus T of cool body. Okay. That is called equals to del T. Okay. And area is the convection area. For example, if I talk about this vessel, okay, if this is my processor, so the surface area, what the square, if I'm saying, if I take as a rough square, so this area of this, like a square, if this is a, like we all know in our basic maths, so this a square is the surface area. So the surface area where my whole heat is, like my wind is flowing, or my where my cooling effect is working, that is called the surface area. Okay. So by this formula, we calculate what is the amount of heat transferred. Okay, in terms of Q. And convection coefficient depends upon, like from fluid to fluid. Okay, that is very different variable. It's a variable. Okay, it's constant. For example, if I talk about for air at different speed, the convection coefficient changes. Okay. Okay. Now see. You can see typical values of convective heat transfer. Okay. So for gases, that is for air and everything. Okay. So it has a range of 2 to 20. You can see 2 to 20. So if I have free convection, what free convection is natural flow. Okay. Not using any external pressure pump, something like that. Natural flow, like our air in the room temperature. Okay. Then we have forced convection. Okay. Forced convection is that now using a blower, pump, something like that. That is external force. Proof index factor is called. So for both, like if you're using gas, like using a fan or something, okay, and for liquid like we're using pump or something. For example, in your four-wheelers, you have a water pump, okay, or oil pump that we call, that is used for for the force cooling of your engine. Okay, so that is used. So it has a range of this. Okay, so if you have high amount of that flow speed, of that fluid, so the range will increase. So there's a range of everything. Like for 2 to 10, 2 means like there's the air is moving at very low speed. 20 is mean that it is moving at a very high speed, so it takes 20. Okay. Then we have for liquid the same, low speed, high speed. Okay, this H or depends upon the speed of the flow as well. Okay, because like if you like you want to cool something, so you blow very hard on it. You don't just just blow a little very slowly. You try to blow it very hard on it. So why you just increase this velocity, outlet velocity of your air, so that thing gets cooled down. So that's why this H value increases as the fluid velocity increases. Okay. Okay. Now we'll come to the main thing. So now what we have is, consider a 3.7 volt 2600 mAh cell that is given over here. A cell 3.7 volt 2600 mAh cell. And your battery offers lithium-ion cell of a battery pack of 48 volt and 45 ampere hour battery pack. Okay. So we have a cell of a battery pack that is 48 volt 45 ampere hour, and the cell rating is 3.7 volt 2600 mAh. Okay. The battery pack powers a 48 volt and 1 kilowatt motor. Okay. I forgot to mention motor, no worries. Okay. With a max peak current of 30 amps. Find the maximum temperature of the cell while continuous operation. Okay. Let us now first understand what we are requiring over here. So we have to first, I'll just check what's the current requirement over here. So if I have, like, see, I have a 45 ampere battery pack, okay, and 48 volt. Now for the standard operating cycle, okay, so we know that P is equals to V into I, okay, and now here we know 1000, that is 1 kilowatt, equals to 48 into I. Okay, so in this question, there's no motor efficiency given on the depth, so I will not take it. I'll take a standard. Okay, but if an efficiency was given, so you have to divide this by the efficiency. Okay, I'll just write this efficiency by mu. Okay, but there's no such thing, so I won't take it. Yeah. So now if I do this, so what I'll get is my I. This is an arrow. Okay, this is an arrow. I is equals to, if I divide 1000 by 48, so I'll get is 20.8. Okay, I'll just take 20.8 amps. Okay, so I'll just take this as 21 amps. Okay, 21 amps. Okay, this is my for a very rated current. That is called my rated current of the motor. And I've given that the peak current that is from the motor controller that we can provide for performance is 30 amps. Okay, so that we have one is the I rated, that is 21 amps, and I peak is equals to 30 amps. Okay, is it clear till now, or you found something that I need to repeat? Okay, thank you. Yeah, meet. So the thing is that if that vehicle is operating at standard continuous rate, so 21 amps is the rating that you require. Okay. So at operating rate, we have something called rated speed and rated RPM, that is called. Okay. So for a motor, if I talk about this 1 kilowatt motor, so its rated RPM will be 1500 RPM. If that motor is working at that speed, so 21 amps will be only taken over here. This is the minimum that the motor requires, like for the working out. Okay. Yes, we will increase the current. Yes, that's why we have 30 amps over here. Up to, yes, exactly, up to 30. So you also have like for the same motor controller, for the same motor, you can have a motor control up to 40 amps. Okay, but you have to see whether your motor can withstand that or not. Okay. Now, what we have is that this is parameter 45 ampere hour. Okay, that we have over here. Okay, so what we have is that battery pack current IB. Okay, that is given as 45 ampere for single charge. That is the max it can go. If we take 1C, 45 at 1C. Okay, 1C. Now, if I deduce what amount of C rating I require, okay, for this, so if I have 45 amps over here, okay, so for time discharge of the battery, okay, no issues. I guess that got cleaned up. So what we had was IR was 21 amps. IP was 30 amps. Okay. Now I'll just make it clear because I have to take you to the ANSYS one as well. Okay. So 45 amps. So if I talk about the C rate, okay, if I use this one, okay, for C rate for this one will be this 45 divided by 21. Okay, oh, sorry, this 21 divided by 45. Okay. So it is around 0.46, the C rate. Okay. If I talk about this one, so I have is, if I use this, so I'm having 30 divided by 45. Okay. This is C rate. Zero point 667. So we have this C rate. Okay. So we get that the max C rate that we're getting is 0.667 C. Okay. So now we have this, like our cells will be working on such C rate, high C rate. Okay. That is 2600 mAh. Okay. So I know if I take this, if I convert this into amperes, it will be 2.6 ampere hour. Okay. And if I make this as, you know, what amount of current that is required. Okay. So what current will be there. Okay. So I'll just require that my current on that basis will be, I take that of I cell. Okay. IC is equals to this 2.6 into 0.67 into, okay, 2.6 into that will be 1.734. Okay, this is 7 amps. So I'll just take this as 1.75. Okay, 1. .75 amps. Now just use this and this to two sides. Okay. So what I have is that my whole thing right now. So what I have is that this is my 1.75 amps. Now I'll calculate the joule heating. That was great. No issues. That was I cell I got was what this current means. Okay, this is the operating current that was required. Okay, while continuous operation that I'm required for testing. For example, if I am reducing that, what I require is like the maximum temperature. What the question suggests is find the maximum temperature of the cell while continuous operation. So maximum, yes, maximum operating current for this specification. If I have this battery pack and I have this control that is allowing only 30 amps of current. Okay, yeah, for a single cell, exactly. So the whole cell is working on this continuously. Okay, at 1.75 amps over there. If, for example, if this ampere rating will be less, if this will be at 30 amps, it will be working at 1C rating, that is 2.6 amps over here. But what we're getting was 0.667. Okay. Now I'll calculate the joule heating. Okay. So this current square 1.75 square into, okay, now what the inter resistance of these cells are around 45 milliohms. Okay, 45 milliohms, that is 10 minus 3. So if I just do this calculation, so what I'll get is 0.1378. Okay, watts, or I'll take this as 0.138 watt. Okay, this is the value I'm getting. Okay, I've taken the joule heating, and now I'll move to my ANSYS workbench because this is the only thing I require, this Q. Okay, this is the ANSYS workbench. Now I'll click this. It is standalone system. Okay, now for geometry. So I've already created a geometry. Okay, that is my SolidWorks. Simple cell dimension that was taken. A very simple geometry. You will see when I open my model. Now I have to add the material. Okay, I click on edit because we don't have the NMC material. Now my cell is an NMC cell. Okay, what I'll do, I'll click here to add a new material. Okay, I'll write this as NMC. Okay, and now For this, I'll add. Now you can see I just clicked on this isotropic thermal conductivity, thermal property. Okay. And right now I have taken this as NMC as new material I've created, and it's only asking me the value for it. Okay. And this is in watt per meter per degree Celsius. Okay. So for a simple cell that I got, like the whole electrolyte, like what we have is that the whole cell, you've seen that you have electrode, anode, cathode, okay, and everything. So all that whole conductivity of that whole cell, what I got from research paper was 5.1. Okay, so it will be taken as 5.1. Okay, different chemistry, you have different differences. Okay, so 5.1 I've taken. Okay, now I'll go back to project. Okay, I've added my the material. I click on edit. That is, so I've added my data. That is my material data. Geometry selected. So there's a green tick over there. And now model. Click on edit. It will take time. By the time, if you could ask me like anything I missed or you want me again to have repeated somewhere.
Sir, while designing the system of the speed and all of that, so we have the power requirement of the vehicle. So how do we decide that, okay, this much ampere of current would be maximum in design would be possible for this controller? Means
Okay.
हमको कैसे पता चलेगा कि वो कितना डिजाइन करना है उस लेवल पे?
Okay, so what happens कि जब हम आप जैसे मैं को बहुत सिंपल चीज बताता हूँ. जैसे मान लीजिए मैं एक आई एम डेवलपिंग इलेक्ट्रिक व्हीकल. ओके, so I have calculated that this amount of kilowatt of rating motor required. Okay, this is the kilowatt rating of motor required. Okay, now I'll go to a motor manufacturer and I'll talk to him that I require this amount of kilowatt of rating motor. This is the torque I require from the motor, and that's of the peak rating. So at that time, he gave me a whole, design report that this max peak current and this rated peak current will be needed for your motor. And on that basis, the whole, design of the motor, you go to a motor controller manufacturer. Okay. And then on basis of looking on the motor graph sheet, performance curves and everything, he suggests you the motor controller that will allot that much amount of peak power or peak current at that voltage rating. Okay, for example, if you're taking a motor of 72 volt, so we provide you a motor control 72 volt. Okay, and then based on your architecture of your motor control and that thing, you design a battery pack. Like you want to go with 1C and 2C. Okay, that's it's 2021. Hisham, sorry. Okay.
So did you model different anode cathode for this or this is whole
No,
solid cell?
this is a solid cell, very basic cell. There's no, like there's nothing inside over here. Okay, so we like what we have is when you deal with ANSYS, so you have to make your geometry as simple as possible. Okay, you cannot go with complex shape. Like if you see if I show you proper cell, then there are very wedges and everything design over there. You cannot see such over there because that will disturb my geometry. Because what happens in ANSYS, there's the mathematical calculations works on each and every node. Okay, and if that dimension is not very simple, so it gets to very complex calculation. It goes on and it takes your whole computation, and you don't have such in your laptop, right? So that's why when you work on such student work benches, that is called our laptops, so we take very simple for analysis. Okay, what I'll do is I have my geometry. Okay, I just open it. I have this geometry. Now material. I have two material. One is NMC, one is structural steel. I'll click on this. I'll go insert material assignment. Okay. Now I go over here, close this. Yeah. And now the geometry to selected. I click on the whole body. Okay. We have this vertex, edge, face, and body. I click on this. Apply. Then I have material. Like you can see NMCs over here. Click on NMC. It's done. See, green tick is over there. Now I'll go to mesh. Okay. So what is meshing for those who have not worked with ANSYS before? So meshing is like, what we happen is when you work on such things. So uh, this is called finite element analysis. Okay, a finite element method. So what we do is that when you are working on like any forces acting on a certain body, or like we are calculating like every point for a whole body. So we know that the whole system is not a very central body. You have lots of atoms over it. Okay. So for example, if at this edge, at this point, I apply a force over here. Okay. So you can understand if I add force over here. Okay, at this point. Okay. So you understand like when you apply force over here, so some deformation will act over here at this point. Not the whole thing will disturb. Okay. So make sure for this software to understand, you have to divide this whole geometry into very small elements. Okay. Elements, or I can say nodes. Okay. So that what it can do, like if, for example, the cylindrical, this will divide the whole into tetragon or any short 3D shape or a 2D shape. So that at that is every phase you can calculate the disruption, the deviation, everything, that you get a very accurate result. Okay, that's why I required meshing. So what we'll do, I'll just change the element size. Element size is like the shape of what the element needs to be divided. Sorry, what is saying, Meet? Just let me open the chat box. How did you assign? Okay, how did you assign? Okay. Nothing, just go over here, insert material assignment. Okay, I'm not doing everything like this. Just click over here, click on apply, then go material name, click here, then you have option. Even you can search somewhere, like you want, you have, see, if you search, you have variety of option to be choose from your library. Okay, that's up to you, but I have already assigned a material from here, so that's why I don't require it. Okay, and I'll just delete this. Yes, go ahead. Sure. I'll come to my mesh. Now on my mesh size. So you have to keep your mesh size very minimum. I'm taking 2 mm. Okay. I'll just go with 5 mm because my laptop is recording and everything. So that will increase my computing time as well. Okay, you can take, I'll show you how to decide which mesh is good. Okay. Click on generate mesh. Right now, ANSYS work with automatic mode. It's very easy. Okay, see. If you see, these are called the statistics elements. Okay, so you can see my whole geometry has been distributed into different elements, like it has been split into various things. Okay, and at this point I can see like my whole thing is split into different uh like forms. Okay, this is called meshing. And now from this, now this is at I've taken is I guess 5 mm. I require this at 2 mm. If I now I have very low elements, like your elements should be in 5 digit to 6 digits. Okay, so you can have a good, analysis. So I just go with this and I click on generate mesh. Okay, so I'm getting 6006. Okay, so if I go with 0.1, like 1 mm, okay, so now my elements are 47320. Okay, and you can see at how many, like small elements my whole geometry is divided. If I just, but this is not very proper meshing. Okay, like there's a very skewed elements over here. Okay, but if I take time to rectify it, so it will take the whole session right now, and I have to show you further things as well. Okay, this is automatic mode I've taken. You have different types as well. Like you want to make a clear mesh and everything, you have different modes you can use. Okay, Okay. Now I'll go on steady state. Okay. What I'll do is I'll insert a heat flow. Now I'll click on these faces. Okay. Now I'll choose this one, this one, this one. Okay. I'll rotate and I want to choose the beneath one as well. This one too. I click on apply. Okay. What this shows that there's a heat flow. Okay. Heat flow over here. Okay. Now what we have calculated was 1.138 watts. Okay. This is my watt rating. Okay. So 1.138 watts, that was my heat flow over here. And from the whole like geometry, surface geometry, I'm getting this. Now what I'm doing is I'll add a convection. Okay. Now this convection will be only used at one side. Okay. So what I'm doing is, like for example, in a battery pack, one side of the cell will be, free to environment. Okay. So that type is that I've taken that surface. Okay. And the rest will be, adjacent to another cell that won't be any free space. So I've taken that way. Okay. At first I've taken one face over here, the side face. And the upper and above, you have in the top and the bottom, you have your cell holders and everything. So you don't have the free air to move around. Okay. Now, what I've talked about here was, see, 2 to 20. Okay. So I'll just take 10 as the heat transfer value. Okay. So if I take 10 as the heat transfer value, okay, convection coefficient. Okay. And now I'll insert thermal to temperature. I just want to know temperature of my cell. Okay, because what the question was, find the maximum temperature of the cell. Okay, so
Sir, did you slice this geometry from between?
no. What happens like it gets like the one I've shaded in my SolidWorks, so it do get sliced over there. Okay, but if you want to slice it into 4 parts as well, you can go to the in the geometry part, click on edit. In space claim, you can all the design explore. You can slice your geometry by using the plane.
Okay, sir.
Okay, so I got it. So my mesh was very see. So what I get a 29 degrees Celsius. So the ambient was 20 degrees Celsius. So my max temperature I got was 29 degrees Celsius. Okay. So you can see the maximum current I got was 29 degrees Celsius or 30 degrees Celsius. So at that, I can see my battery design is safe. Okay. Now I can do one more thing. Okay. Either I can keep this as 5. Okay. And now I'll solve it. And let's see. 5 means that it is at proper room temperature. Like there's no even flow, like very, like even the battery is not room, is stable over there. It takes time as more fine mesh, like there's two things, fine and coarse mesh. Okay. So fine mesh means that your element size is very reduced. Okay. It's very, even the, the element size and quality is very fine. So that is called fine mesh. Right now, this is at mid. Okay. And coarse mesh is like the one which I showed you with 5 mm. Like you can see the line is very broad. That is called coarse mesh. So at coarse mesh, the computation time is very slow, very quick. And once you go with fine mesh, so it increases computation time, because now the whole computation or the speed have to work on evaluating every node element at what temperature, what point would be that based on this. Okay. Now what I've done is that at same continuous running current operation, I've reduced the flow of air or the heat transfer. Okay, so let's see. Miss Mayur Pandey, you want to annotate the screen. See, now what happened when I reduce my heat transfer convection rate? So the temperature increases 37 degrees, or I can say 8 degrees more. Okay, so you can see like that. Now I've taken the one was I've taken 10, now 5. Now if I what do, if I take this as again 10, okay, and now what I'll do is like I'll operate the battery at 1C rate. That is to 26 degrees Celsius, 2.6 ampere hour, 2.6 amps. Like now, if I do that, so 2.6 into 2. So what I'm doing, if I explain you properly, so here what we had was according to this and this, we had 0.67 C rate. Okay, C rate. And now if I want to take it very max, I just want like what current I was getting from this was 1.75. Okay, so for that basis, for the whole question, okay, now 1.75 amps. Okay, and for that, and for very if the battery pack is not moving somewhere, so my max temperature was 38 degree Celsius. Okay, this is the answer. Okay, so for the whole question, I got my answer through analysis. That was very practical based. So I can assume that then my battery pack is not going above 50 degrees Celsius. So that is safe. Now what I do is, like if I just take this for individual cell, okay, I'm not considering this battery pack. Okay, so at one rating of this cell, okay, so if I just calculate the Q, okay, now I'm just going beyond the question to for demonstration purpose. I'll take this 2.6 square into that entire resistance. I'm taking R. Okay, that is 45 milliohms. Okay, so what I'm getting is 0.3 watt. 0.3 watt. Okay, now I'll go back to my workbench. I'll click on heat flow. Yeah, it's there. Now I'll make this as 0.3 watt. And I'll just click on solve. Okay. For the same, now getting 39 degrees Celsius. 39 degrees Celsius. Okay. So from that, I can approve that my battery working temperature is 39 degrees Celsius. So by the same way, you can, just change the heat joule effect, that is in watt. Okay. The heat flow, and by the convection, you can analyze your battery performance. Okay, like what temperature gradient it can reach max up to. Okay, any questions?
Sir, I am trying this right now. So in my system, there is no option of changing the size of the mesh. So how can I get that?
Changing size of the which software, which ANSYS you're using?
Same one, 2021 student version.
So you're not getting element size over here.
Yeah,
Defaults. Click on the sizing. Okay.
I'm not getting that dialog box itself.
The dialog box itself. Okay, okay. So you have to change this layout. Okay.
Okay, 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 sir.
You have used it for first time?
No, sir, I used it earlier, but I forgot from this where because I didn't face any issue first when I used it earlier. So this time
No
this is
issues.
not showing. So
No issues, mate. Okay. So any questions like anybody want to ask about this? Like if you ask me what red lines are, so this blue shows that is the place where uh, that air is flowing around. That's it. Okay. And this red shows the maximum temperature. As at half of the geometry, the half of the surface, you're getting this airflow. And the other half you're not getting, that's why This shows that at this point it is you're getting 38, 39 degrees Celsius. And at this point, okay, just at this point you're getting only minimum 38.3. Okay, so this side will be more hotter as compared to this.
Sir, here we considered the isotropic heat, means we are considering the average of all the materials, right?
Yeah,
So
isotropic
isotropic.
means that it is standard. It's ideal actually, isotropic.
Okay. Okay. And if we want to model that different anode cathode, then it would be quite complex in this, right?
Yeah, because then we will see like even my system has 8 GB of RAM graphic card, but it took very high computation for this such simple model. Okay, so if you because this is solid geometry, if you have cathode anode inside it, will take you, like a workstation to work on it.
Sir, in actual battery pack, if we suppose we design a battery pack and then we want to simulate that whole battery pack with the cooling effect and all of that, then how can we means go for it? Means
Then you have
we
to go
did.
with ANSYS Fluent. You have to perform CFD. Like if you're going with having, forced induction, that is called a fan flow and anything like that. Okay,
Hmm.
or even natural flow. So for example, if you're taking cylindrical cells, then you have to form that simple model of that whole cells in an alignment with holders and everything, a very basic model. And you have to
Hmm.
apply that for each cell. You have to add that what energy generating for it, Joule heating effect, and then you have to add a laminar flow of the air, okay, with at convection rate, okay.
Okay, sir. So, sir, if someone is looking for a means in industry, someone wants to join as a BMS battery design engineer. So, what level of skill one needs to have means to carry out this simulation?
Okay. So first thing he needs to understand about is the way the performance of cell works. Okay. This is the basic one. Okay. Like when you optimize the cell temperature. Then if you're working on the battery pack cell design, you have to know about the chemistry that you're dealing with. Okay. You have to focus on the discharging charging. Like right now, I've worked on the operating current. Okay. Now about the discharge current, the charging current. On that piece, this will be applied, and you will require the ANSYS fluent for deriving, the if you're using a liquid cooling or if forced air cooling. So for that, when you apply that, so what will the temperature cell will be used? So what happens? You can even use for liquid cooling. You can add, that convection over there. But if you want to see the actual flow of that whole laminar flow of that whole, then you require ANSYS fluent. ANSYS fluent is used for fluid dynamics or fluid mechanics, everything. And there you will be getting the thermal quantities.